Hello everyone, this is Mr. Spurk, and this is your Chapter 14, Section 4 notes, all over gases, mixtures, and movements. So we're going to start by talking about Dalton's Law. Gas pressure results from collisions of particles and a gas with an object. If the number of particles increases in a given volume, more collisions are going to occur. If the average kinetic energy of the particle increases, more collisions occur. And in both cases, the pressure increases. Particles in a mixture of gases at the same temperature have the same kinetic energy. The kind of particle is not really all that important. The contribution each gas in a mixture makes to the total pressure is called the partial pressure exerted by that gas. So the total pressure of dry air is the sum of the partial pressures of the component gases. So if we look at the volume percent of air, you see that we have nitrogen, oxygen, carbon dioxide, and then argon and other gases. And they add up to 100%. And then if we look at the partial pressure, this is the pressure that each gas exerts by itself. So nitrogen has a partial pressure of 79.11. Oxygen has a partial pressure of 21.22. Carbon dioxide 0.04, and argon and the others 0.95. And they add up for a total of 101.32 kilopascals, which we know is our standard pressure. So in a mixture of gases, the total pressure is the sum of the partial pressures of the gases. The chemist John Dalton proposed a law to explain this. Dalton's law of partial pressures states that at constant volume and temperature, the total pressure exerted by a mixture of gases is equal to the sum of the partial pressures of the component gases. So the total pressure, or P total, equals partial pressure 1 plus partial pressure 2 plus P3 plus P4 plus on and on and on and on and on for all of the gases that are involved in a mixture. Each component gas exerts its own pressure, independent of the pressure exerted by the other gases. So the pressure in the container of heliox on the left is at 500 kilopascals, so we have helium and oxygen in there, is the same as the sum of the pressure in the containers of helium and oxygen. Helium being 400 kilopascals and oxygen being 100. So using Dalton's law of partial pressure. So air contains oxygen, nitrogen, carbon dioxide, and trace amounts of other gases. What is the partial pressure of oxygen at 101.30 kPa of total pressure if the partial pressure of nitrogen, carbon dioxide, and other gases are 79.10, 0.040, and 0.94 kilopascals respectively? So let's remember that the equation for partial pressure is, in this case, P total equals the partial pressure of O2 plus the partial pressure of N2 plus the partial pressure of CO2 plus the partial pressure of the others. And I realize those little subscripts are pretty poor, but they're pretty tiny on the screen here, so it's kind of hard for me to write. So now we have all these pieces of information except for the partial pressure of O2. So we're just going to plug these in. So we have 101.30 kPa equals the partial pressure of O2, because remember that's what we're solving for, plus 79.10 kPa plus 0.040 kPa plus 0.94 kPa. So the way I usually solve these is I bring down where I'm going. So 1.30 kPa equals the partial pressure of O2. And then I'm going to add up these values. So 79.10 plus 0.040 plus 0.94 add up to 80.08 kilopascals. And then we need to subtract 80.08 from 101.30 to leave us with our partial pressure of O2. And that gives us a value of 21.22 kilopascals. So the partial pressure of oxygen is 21.22 kilopascals. So now we're going to move on to Graham's law. If you open up a perfume bottle in one corner of a room, at some point, a person standing in the opposite corner will be able to smell the perfume. Molecules in the perfume evaporate and diffuse, or they spread out throughout the air in the room. Diffusion is the tendency of molecules to move toward areas of lower concentration until the concentration is uniform throughout. So if we look at the cylinder of air and a cylinder of bromine vapor are sealed together, and the bromine vapor diffuses upward through the air. And after several hours, the bromine vapors reach the top of the column. So they diffuse because the concentration of bromine is very high down here and very low up here. So the bromine is going to want to diffuse from high to low pressure, and so eventually it becomes uniform. It spreads out, much like the perfume will spread out throughout the whole room. So during effusion, so that's effusion, a gas escapes through a tiny hole in its container. With effusion and diffusion, the type of particle is important. Gases of lower molar mass diffuse and diffuse faster than gases of higher molar mass. So Thomas Graham's contribution. Graham's law of effusion states that the rate of effusion of a gas is inversely proportional to the square root of the gas's molar mass. This law can also be applied to the diffusion of gases. If two objects with different masses have the same kinetic energy, so that means they have the same kinetic energy, they're moving with the same energy, the lighter object is going to move faster. Because the rate of effusion is related only to a particle's speed, Graham's law can be written as follows for two gases. We'll say those gases are A and B. So the rate of A over the rate of B, and now this part is a little tricky to remember, it equals the square root of the molar mass of B over the molar mass of A. So if we look back at the left side, we see that it's a rate of A and on top and rate of B on the bottom. But when we do the square root, the molar mass of B is on top and the molar mass of A is on the bottom. So we can compare effusion rates. So how much faster does helium effuse than nitrogen at the same temperature? So we're just going to plug in to that equation. So we have the rate of helium, because remember it's asking us how much faster does helium effuse than nitrogen. So we're comparing helium to nitrogen. And remember, it's going to be the molar mass of nitrogen on the top divided by the molar mass of helium. And then we're going to take the square root of that value. So when we calculate this out, we get 2.7. So what that means is that helium effuses 2.7 times faster than nitrogen. So in review, in a mixture of gases, the total pressure is the sum of the partial pressures of the gases. Gases of lower molar mass diffuse and effuse faster than gases of higher molar mass. Dalton's law is P total equals P1 plus P2 plus P3 and so on and so forth for all the partial pressures. And Graham's law is rate of A over rate of B equals the square root of the molar mass of B over the molar mass of A. As always, all the information on these slides has been acquired and adapted from Pearson Chemistry, 2012 edition of the textbook, the resources CD, and pearsonchem.com. Have a good rest of your day.